Let's move on to the properties of expectations. So, okay, we introduced the definition of expectation and took a brief look at the change of variable formula, which I don't understand very well. But we have to move on. So the first property is positivity. If x is a positive random variable, then the expectation of x is also positive. The second is monotonicity. If we have x larger than y positive, expectation of x is larger than the expectation of y. Okay, correct. Then linearity. Given x and y random variables a and b in R, the expectation of ax plus by can be, it's the same as a times the expectation of x plus b the expectation of y. So if we compute the expectation of all these things, we get the same result as if we multiply the expectation of x by a and we multiply the expectation of y by b and we sum them. Okay. Insensitivity. Does it means that if we have x equal to y almost surely, then the expectation of x is the same as the expectation of y? Of course, positive as always. My question now is, which problems can we face if we have negative random variables? Does it make sense to talk about negative random variables? The fifth one is monotone convergence, which is the following. If we have a positive sequence of random variables xn increasing to x, then the expectation of xn increases to the expectation of x. Fatu's lemma for expectation says that given a sequence xn increasing to x, no, it's not increasing to x. We simply have this. Well, it should have a limit x, but the expectation of the lim_inf is less than the lim_inf of the expectation. Okay, so it doesn't, here we don't even have a limiting variable x. here we have dominated convergence theorem. If x is bounded above by y in absolute value, almost surely, and y is integrable, here it's written like this: if we have a sequence xn such that for any n, xn in absolute value is bounded by y, and the expectation of y is finite, then the limit of xn, of the expectation of xn, is equal to the limit, is equal to the expectation of x, right? Nope. Here it says that the limit of the expectation of xn is equal to the expectation of the limit. Well, actually the other way around, but it's the same. Then we have bounded convergence, which is the same as the dominated convergence, but instead of y we have b, which is a constant. Yes, so these are the properties of expectation, which derive by its definition as the integral of x with the measure p. In this remark we have the following: if the expectation of indicator of h, the expectation of x times the indicator of h, so the expectation of x restricted on the set h is greater than the expectation of y restricted on the same set, then we have that the x is simply greater than y almost surely. So by this we mean that all the possible values that x can take are larger than y. So for example, I don't know, consider y equal 1, 2, 3. This is its distribution. And x is equal to 4, 5, 6. Then the expectation of x is greater than the expectation of y, but this simply, I mean, in this case, x is greater than y, because all the values that x can take are larger than y. And at least this is how I interpret this. I mean, I interpret it in this way. Now, let's write a theorem which describes the distribution, the expectation of a function of a random variable. Let x be a random variable taking values in space C, which is measurable relative to h and e. if mu is the distribution of x, then the expectation of a function, well, we should also talk about the function or not. Here it is, it doesn't, the expectation of a function applied to x is simply the function integrated with the measure mu, right? No. Yes. The function integrated with the measure mu. So the expectation of a function of a random variable is the integral of the function with the distribution of that variable. Conversely, this holds for some measure mu on the space E and for any f. If this holds blah blah blah, then mu f is equal to expectation. No, then simply mu is the distribution of x. So this is the central thing here. And if we find that, if we find this relationship for some mu, it means that mu is the distribution of x. Okay. And here I made an example. For example, consider f to be 2x. I don't know if this makes sense. So that the expectation of 2x is mu integrating 2x. In other words, the integral of 2x using the measure mu, well, let's write it like this, over E, over omega, or over E, over omega, I think, because the random variable is integrated over omega. This is a capital X, I think. No. Let's leave a question mark here. And the proof is the following. The first part is the change variable formula. Is given by the change of variable formula that we saw before, and I should try to reflect a bit on how it is connected to this. Change of variable formula, let's recall. h of f of x is equal to the integral over still f, right? No, here it's e u dy f of y. My question is, why do we have two different sets here? And what is the interpretation of this thing? Second part, if this formula holds, so then it also holds for f being the indicator function of some set or some event. For any h. And the measure of h is simply a distribution of x. In other words, what we have seen in the past, this thing here, probability of x, of the realization of x belonging to the set h, written this way, well, actually, here it writes it in this way. If h is the expectation of the indicator of h, no, it's mu of the indicator of h. It's the measure of the indicator of h which is equivalent to this applied to x. I am thinking now to translate this formula using the change of variable formula. This is the thing. What is the central idea? The central idea is that we have a measure and we have a function of a function. And here this is equivalent to using another measure with another function. We have translated into, rather than integrating the random variable using p, we integrate another function using the distribution. Actually, we integrate the same function using the distribution. I think this could be the meaning of the result. Let's make some examples. Of expectations. The first one is the variance. The variance of x is the expectation of x minus x bar, x minus the expectation of x squared. Mu tilde r, this is the Laplace transform minus rx, or in other words, the integral over r plus exponential minus rx mu dx, yes, which is also called MGF. And then we also have the Fourier transform, which is the characteristic function. And this time we have the integral over r exponential minus irx mu dx. So all these are examples of expectations. And they are related to the previous theorem that we have seen with this formula here. So for example, here f is exponential minus rx. And now, is this useful? I don't know. Well, here it writes it more explicitly in the following way. Integral over r mu dx cosine of rx plus I sine of rx, no, plus I, which multiplies the integral over r, mu dx sine of rx. Let's go with the MGF for discrete random variables. This is a little z to the x. This is the infinite sum from 0 of the probability no, of z to the n, probability that x is equal to z, no, n. Let's repeat it. The expectation z to the x is the infinite sum from a crash. N equals 0, probability that z to the n, probability that x is equal to n. And these formulas are used to derive the moments of random variable, which are mean, variance, and if you want also skewness and kurtosis. I don't remember the name of this thing. I mean, it's also MGF, but I think it had a particular name for discrete random variables. Finally, we have the covariance, which is another expectation. Expectation of x minus the expectation of x, y minus the expectation of y. Let's discuss the optimality of expectation as an estimate for the values of the random variable. So we have something like this, say squared, and we want to minimize this. So we have that x differs from a constant, and we consider the squared deviations, and we want to minimize the squared deviations of the values of the random variable from that constant. So for example, let's say, I don't know, so this is the random variable and this is the expectation expectation of x, and we want to minimize all these distances. So we want to find the best line, yeah, as an estimate for the values of x. So if we derive with respect to a, what do we have? This is written this way here in the notes. Minus 2 x omega minus a equals 0. Okay. Now we can write here this, we can take this thing out, and here we simply have x of omega minus 2. Well, here it writes it like this. Splitting the integral, and this is again 0. And solving with respect to a, we obtain that a is well, this should be same thing. So here we cancel out. A is the integral over omega, x of omega, integrated with b. And this is nothing but the expectation of x, by definition. So let's recap. We wanted to find a constant which minimizes the distance of all the values of x, of the squares. Well, so we derive this, like if you remember when you optimize a function, let's say, I don't know, we have something like this, we want to find the derivative which is 0 to find the maximum or minimum, and since this is a quadratic function, we have something like this, so we know it's a minimum. And so when we derive this, we consider this thing together, we just put a minus 2 in front. Why? I mean, I remember that x squared, 2x, blah blah blah. So why do we have a minus? I'm really bad with derivatives and integrals. In any case, we have the derivative and then we solve for a and we realize it's the expectation. Okay. Now let's just briefly recall before closing. Let's recall some inequalities. Markov is the following one: the probability that x deviates from its expectation in absolute value, probability that x deviates from its expectation by a value larger than epsilon is equal to the expectation of x over epsilon. Chebyshev or Chev, I don't know. I'm quite dumb. This was Chebyshev. But okay, so the probability that x is larger than b is bounded above with expectation of x over b, while the probability that x deviates from its mean, now this makes sense because this is bounded by the variance of x over epsilon squared. And then Jensen, the expectation of a function of x is less than the function of the expectation of x for f convex. No, it's actually greater. And then here it says general expectation of a function of a random vector is greater than the function of the function of the expectation. For f continuous and concave. And okay. Okay, wait. So here we have the other way. If it's concave and continuous. Okay, I think we can close here. We have seen the properties of expectation, example of expectations, why the expectation is an optimal estimate for the values of a random variable, and we recall that these final inequalities which are very useful in some proofs. Okay, let's pause for a while.